Of all the equations that have been created to calculate flow velocities, and especially mean flow velocities, so the average over the full depth of the flow, Manning's equation has probably been used more than any other one. So Manning's equation is a modification of Chazy's equation. Manning realized that Chazy's C sub z, so the Chazy coefficient, is a function of depth. So why do we suppose that is? Because it's this unitless constant, and it's supposed to relate to kind of the reciprocal of the roughness, right? So Chazy's coefficient gets bigger if the roughness gets smaller and the flow is able to move more rapidly. So why is this? So let's start out by just writing out what Chazy's relationship is. Chazy's relationship says that the mean velocity is equal to some coefficient times u tau, which is the shear velocity, which equals this coefficient times, in steady uniform flow, the square root of g hs, the slope. And this h term is the really important one here. So let's draw a picture of a channel. So we have a bed here, and that bed has some roughness associated with it, maybe because there's some grains of sand or gravel on the surface. And then on the top, we have an open water surface. We can draw like that. And then at some point in the middle here, let's start thinking about what the flow conditions are, and specifically how much of the roughness that flow feels. And so what I'm going to posit right now is that the flow that's at the bottom is going to feel a lot of the roughness, because these flow lines have to go up and down and over each of these individual bumps. Whereas the flow at the top is going to be move pretty much free of roughness. There we are. That's much less wavy. So on the bottom is more roughness impact. And then at the top is less roughness felt. And that's because this higher up flow is cushioned from the roughness by this flow that's lower down. So the thing with Chazy's equation is it's trying to solve the mean flow velocity, right? And by the mean flow velocity, what I mean is that u bar applies to this entire flow. So u bar, you can think of it as the velocity at the bottom plus the next velocity plus the next velocity plus the next velocity, divided by the number of boxes you subdivide this total velocity profile into in order to achieve that mean. So what that means then is that the higher the flow is, so the thicker the flow, the more fluid is farther from the rough no-slip boundary, which is the bed. Make sure that you can see that that's a G. And because of that, then you start to take into account more flow that isn't really as affected by that roughness, and therefore the flow velocities end up getting faster. And so what we'd expect is that the Chazy coefficient would go up as the flow depth goes up. And as a matter of fact, if I scroll up and remind us that indeed Gary Parker found this weak relationship to the power of the 1/6 between this flow depth and the Chazy coefficient. So indeed, that is the case. And if we think about this 1/6 power that's up here, and this power of 1/2 that's here, so then if we have Chazy coefficient is proportional to h to the 1/6, then we end up having h to the 1/6 times h to the 1/2 from the square root here. And so that gives us something like h to the 2/3 times g times s to the 1/2 from the square root term right there. And indeed, that's exactly what Robert Manning found. So by combining many different equations and observations that were available in the 1800s while he was working as an engineer, he came up with his own empirical equation for mean flow velocity through work extending all the way into the 1890s. And in the early 20th century, this formula was generalized and popularized as follows. And so we have over here, u bar is equal to this, and there's supposed to probably be a new line right there. And I think I forgot to put the little 2 slashes in LaTeX when I was writing this. And so I'll just write another u bar there. And so the reason I have this here is this is the hydraulic radius that we talked about last time. And if you remember, if we have a channel like this and we have the depth and the width of the flow, then, and we have the area, which is equal to in a rectangular channel just h times b, the hydraulic radius is equal to the area over the wetted perimeter, which is 2 times h plus b. But if b is much greater than h, what happens then is that we ignore this factor of 2h here. We ignore that h up. What we do is we ignore this 2h down here, and then we end up just having h times b. So if we multiply h times b, then h is still important, but if it's just something that's added to b and it's much smaller, then it's not as important, right? Because something small added to something big, it becomes unimportant, but if you multiply something big by something small, that small number can still scale it significantly. And then h times b over b just becomes h. And so what we typically do then is just for channels that are much wider than they are deep, which is the vast majority of natural river channels, we just convert this hydraulic radius into a depth. And so this is the form of Manning's equation that we're going to think about and use. And the other thing we can see here is that there's this term n. And this is called Manning's n, and that's a friction factor. And so as you can see then, as the friction gets bigger, because it's in the denominator, the velocity is going to get smaller. So how do we know what this friction factor is? Well, one kind of fun way that we can figure it out, and honestly one of the best ways, is what are called the Manning's n picture books. So this is literally what it sounds like. This is possibly the first time in a science class you've encountered a picture book. So although there's another lovely picture book, a really classic book on fluid turbulence. It's a gallery of fluid turbulence. You should check it out if you are interested in turbulence in general. But these picture books are photographs that have been taken of different floodplains and channels and other features after engineers and geologists have calculated what Manning's n should be for those. And so they give you this idea where you can kind of flip through it and see what your landscape looks like and see which Manning's n from these other calibrated settings might be the best value. And there are also tables for the same purpose, and you can just search Manning's n table online. In fact, that's how I came across this one. And so you can see something like this, where for like a clean, straight channel with no deep pools, and that's the Manning's n is something like 0.03. On the other hand, if we go to like a floodplain with dense willows that in summer so therefore that have their leaves on, the Manning's n is 0.15, and so this is a factor of 5 increase in the roughness, so in the flow resistance. And so these sorts of tables can also be quite useful. And the way that these work, both these tables and these picture books, is that someone rearranges Manning's equation. So we have, for Manning's equation, we have u bar equals 1 over n, Manning's n, and then which is for flow resistance. H to the 2/3, S to the 1/2, and then you can imagine you just bring n over here, bring u down there, just so this shows up a little bit better. I'm going to switch that to red. So bring n up here, and bring u down to the bottom there. There we go. We see it's not the same thing is creating those letters now. And as a result, you can actually then measure the mean flow velocity, measure the hydraulic radius or the depth as I've shown here. So just a little note, or RH, and the slope of the channel. And then based on the depth, slope, and velocity, you can actually back calculate what Manning's n should be. And then either by characterizing the landscape and putting it in a table, or by working through the picture book, you can get that value. So the next question that we have is one of just like the quick idiot check. So does Manning's equation behave properly at the limits in which there's no water in the channel, so the depth equals 0, or the channel being filled to the brim with water, H equals H bankful? Let's find that out. So first off, we have U bar equals 1 over n h to the 2/3 s to the 1/2. And I think it's pretty clear that if h equals 0, then U bar also equals 0, because there's a 0. Everything multiplied by 0 becomes 0. Check. Great, it works. If h equals hbf, which is the bankful, so that's going to be the highest level of the flow when the flow is still in the channel, then U bar is going to equal h to the 2/3 s to the 1/2, so where this is hbf, over n. And if hbf is the biggest h, then this is the highest flow velocity as well. So check. Good. That's also helpful. So then, what we have to think about as well is whether the units of n, of Manning's n, are appropriate. So, in thinking about this, let's see what those units should be. So we have U bar, which is, let's say, meters per second, equals 1 over n. Then we have meters to the 2/3, and then slope is meters per meter, right? So that is unitless, so we'd have nothing there. So then what we do is, let's rearrange this equation. Let's say then, and I'm going to put brackets around all of these terms that are units. And so then we have n, the units of n, we'll just leave it like that. Units of n are going to be equal to seconds per meter, meter to the 2/3, equals seconds per meter to the 1/3. So that's actually pretty hard to understand. There's not really a very good physical explanation for this, and as a matter of fact, this bothered Manning too. He started out building his equation just for purely practical purposes, but the fact that there are these strange units represented by this coefficient means that there's probably something missing in this equation, and there might be some scale dependence in Manning's n, so that a value of Manning's n for a river that's a few meters deep won't work for a river or a flood that's something like 300 meters deep. It's possible. So there's been some work to try to generalize Manning's equation and to try to also come up with other and better ways to characterize the roughness and the flow velocity profile. And some of those are what we're going to discuss next. And so just last thing I'll leave you with is that Manning's equation is useful. And it's widely used, but dimensions exist for the coefficient. And the physical meaning is a little bit unclear. So that's the piece of concern in using this, but this is used by engineers all the time, and you should feel free to apply Manning's equation to any river system you want. It's used so extensively through river systems, and I've in fact used it in my own work that I think that that's really no problem. And once again, just remember that this came out of Shazy, but then the deal is that because the deeper flows are farther away from the roughness elements, then we actually have a reduction in the effective roughness as the flows get deeper.